Okay, back to the business. So this exercise is actually for you to work on it at home. Please go through this one. So since it's the only way to learn electronics is to make lots of exercises. Do the laboratories, test it yourself, get your fingers burned, burn some transistors. They're cheap. Just do it. There's no shortcut on this one. So this is very practical skill. And yes, you also might actually consider you will be electrical and electronic engineers or something like that, right? So it's electronic communication. What is the other degree? Okay, good. Yeah. So electronics. Why we do everything in China? Have you thought of why we actually do everything in China? Cheaper. But how long? So you are the generation who will be designing electronics in Europe again. That's my forecast for the future. Otherwise, I will move to China myself. They'll be winning. But anyways, this is practical example. Okay, there's that 4 watt that should be actually consumed on 10 ohm load. This is a A-class amplifier with the voltage source, and then it also have what is this one? You should know that. That must be the current source, right? So key is to have a common current for both transistors. So basically, it's current mirror. So you set up the current on first one, and then the Q2 is actually following whatever the current in Q3 is, something like that. But anyways, so go through the calculations yourself. You know already that in order to get the 4 watts on load, you need to consume or design that current source for 8 watts at least, and also that the amplifier transistor also for at least 8 watts. Okay. And yeah, there are these calculations. Go through the calculations yourself. And then some study material. I would like to make an advertisement now about the one of my favorite books, Horowitz and Hill, The Art of Electronics. My favorite. So this is just an advertisement. So. This is very practical electronics handbook covering lots of real-life circuitry, including examples of very bad designs that you can actually make the kind of error finding yourself. So go through that book, you will be a specialist in electronics. And it also covers the mixed signals, not just analog electronics. Starts from the transistors, diodes, that kind of things, and ends on the mixed signal circuitry. All right, but then let's go a little bit forward on the topic. All right, so B class. So basically, B class is kind of combination of two transistors that are used to push and pull. So it's quite similar to in digital logic. You have this push-pull kind of output stage. Yes, that's quite similar to that one. Actually, when I was young, that was a long time ago. I'm a dinosaur. when I was young, there was what is that? H logic. The the MOSFET logic circuits. You could use some of those as linear amplifiers. Okay, pretty crappy ones, but anyways, you could use them. For example, a simple voltage follower could be done with a amplifier or a gate, HCL logic gate, by just taking the input and then taking the output to the same input, and that's a follower. Okay. But here we actually have the different amplifiers for the positive cycle and the negative cycle. So that's the definition of class B. And basically, on the positive cycle, the B plus stage is active, and negative cycle, the B minus is active. Okay. So there are some, say, classical limitations or kind of caveats on this design, which cause some problem on the design phase, but if you tackle those, you will get a quite nice and quite efficient amplifier. So you can get as efficient as you get with the linear amplifiers on the B class or AB class. Okay, that's a basic circuit. Put that one here. So B class amplifiers. Well, the classical. Basic idea is to actually have a signal source, VI, the current limiting resistor, since we are still running, oh boy, I'm running out of space already. Let me start with transistors. So we have a NPN transistor right here, which actually takes care of, maybe I should actually draw it like that. Yeah, current limiting resistor to set up the base current. And then we have, so this amplifies or is a follower, voltage follower for the positive cycle. Okay. But this one, as you know about the bipolar transistors, they amplify only on the bipolar signal sources. You cannot get the negative signals here. This just, doesn't work. Since that is a diode here, which defines the current, which is then amplified by the beta of the amplifier. And if you have negative signal here, this diode here is actually on the wrong direction. It doesn't conduct anymore. So we can fix that problem by adding a PNP transistor here. Oops. Minus V, C, there. And same signal source. Good. So on positive half cycle, that one conducts. On negative half cycle, this one conducts. But there's a limitation. about the limitation later. So basically, the requirement here is that we have matched transistors in order to get the same current amplification. Since we have only one resistor here, which basically defines the current for both one, it means that the beta in here and beta in here must be the same, as close as possible. Otherwise, this does not quite work. But anyways, that's something that the manufacturers have solved that problem. So there are complementary paired transistors available still until the supplies last, something like that. Okay, so and of course the speed characteristics should be equal, and also the power characteristics, and of course the aging and that kind of thing should be also the same. So they basically should be the same. This is just the NPN and this is PNP, but otherwise the same. Which is hard. It's not that easy anymore. That's why your parents' first good stereo systems were so expensive. And because they actually read Pioneer there, or some other, or some other brand. All right. But more serious thing is that it doesn't cover that there yet. Oh, yes, it is. Yes. Okay. Both of these actually require the voltage to go big enough to have any current there. Right. So basically, we are talking on this these curves, VBE. We are talking about this region. Small signals. This system really does not work on the between the plus minus VBE. So there's a dead zone. Okay, then there's a very good question. How much does this dissipate power without a signal? No signal. What is the power dissipation? Zero. No signal here, meaning no current. There, meaning no current on the collector. Well, if there are no currents there, there's no current to the load either. So if there's no signal, this is shut off. That's nice. When you turn on the power, you don't start heating the room yet. You just wait for this signal to arrive, then you start heating the room again. But there, that's kind of a problem since let's see. Just looking for where is the problem better ways. But anyway, so I will cover it here. So fundamentally, if you take a look at the kind of the transfer function of AB or B class amplifier. So that's the positive and that's the negative side. We have here input power, input signal, and then the output signal. The same thing as in the previous A-class amplifier. It was quite nice since actually it covered the region of the zero also quite nicely. But here we are actually covering something like that. The standard, diode curve, more or less, like that. So we have a dead zone. Otherwise, it's a linear, but there's a dead zone here, which is not good. If you run a sinusoid signal, so if you're if you have a sinusoid signal, and then measure the oops, that's VI. Measure the output signal right here. So these parts are not covered right, so it actually goes, the signal goes like that. So that's this crossover point, which gives the crossover distortion. I remember this one actually comes later on, but I think this is a good place to talk about this one. Okay. So fundamentally, that slide is about the positive input. Okay, that's the equivalent circuit there. So we have the voltage drop. So should I actually redo it? So the equivalent circuit of the positive input. So we have positive input, the current limiting resistor. The lower transistor does not conduct. It's on off state. Positive, this was PNP transistor. So it's open circuit basically. Open circuit, doesn't conduct, no current on the base. But the upper half, there's a voltage drop, so that's VBE, or V gamma, I think. On this marking, this is the V gamma, meaning the voltage required for that transistor to turn on. There we go, and then there is the load. Okay, something like that, still the load. And here we have a current source. Well, I'd mark it like that. Plus VCC, and this is the collector current, which is the same as beta of the first transistor times this current. Good. And the current to the load. Well, to be exact, current to the load is IC plus IE, right? But since we are doing the power things, that's roughly just 1% of the collector currents. So it's negligible. This is engineering, this is not science. Okay. And power gain, where does the power gain actually come? So basically we have the voltage gain here is voltage gain is 1, more or less, if you take care of the so then this is negligible. If this is conducting, then this is actually 0. Okay, and then we have the current gain. So we have the voltage gain is 1, and the current gain is actually the same as the current amplification of this transistor here. Simple. So we have power gain of beta. Right. So, okay. That actually gives you some ideas now. So if you want a power of 10 watts here, okay, and you have 100, this beta is 100. Then you need some power also here. Right. You need 1/100 of the current of that one, which is still quite substantial. So it's 100 milliwatts of input power, signal power on the input in order to make the 10 watts here. Okay. So that's kind of easy way to mismatch the amplifier and see why it doesn't amplify as much as I wanted. Because you are not, you cannot drive this one with just any amplifier. For example, 100 milliamps. You take a general purpose operational amplifier, which gives 10 milliamps. Okay, don't expect big power output if you're running it on the wrong power inputs. But anyways, we got the power gain there. Negative is actually similar, but the polarity is just opposite. So basically, we have the power gain, which now also means that, okay, we have to have the beta 1 and beta 2 as close as possible to each other. Otherwise, you will be getting more power on either positive or negative cycle. And that's also one sort of distortion what we are talking about here. It's kind of a symmetry distortion. It shows up, okay, in amplifier. Oh, that's how the those charts actually get broken. Okay. I owe you a penny. Okay, so that's an audio electronics. If you buy a hi-fi system, it always tells about total harmonic distortion. That's one source of the total harmonic distortion. Unbalanced the output stage. Good. Okay, what else? Output voltage limits. Okay, so the voltage limit here, well, it's a transistor. You can run this part only up to the saturation voltage. VC is at 1. Same thing here, only up to the VCSat. And that's another place for total harmonic distortion. Clipping. You're running it too close to the VCC. It starts clipping, which is good if you are playing a guitar on a heavy metal band. Distortion is good. Alrighty, so the same thing also on the negative side. Well, beware, it's PNP, yes. Would you elaborate why we should be aware of this PNP other than polarity? There's this PNP, yeah. Yeah. Mm-hmm. Yes. And why is that? There's actually some physics on it. How the P and N are doped. Okay, the doping materials of P-type semiconductor are more expensive than the N-type materials. That's one reason. Another one also is it's about how you can make a really nice equal doping of all the areas. The same actually goes also with this field effect transistors. It's easy to make depletion enhancement on the MOSFET on N channel, but on P channel it's almost impossible or very expensive. Okay. So there we have the dead zone. I like my picture better. And the crossover distortion. And that's basically the why the B class itself, it's quite not often used. I don't think that there will be any, well, maybe very, very cheap amplifiers, for example, or for the where you yell all the time, for example, on those megaphones. That could actually use the B class amp, since there's a lot of distortion in any case. Okay, but this is not acceptable, since for big signals, this might not actually, there's a chance that you don't even hear it. But think of a small signal. Now you are basically hearing it. So it affects more on the small signals, and you get a real distortion there. You can hear it. And of course, when the signal is small enough, it just cuts off. Okay, even worse. But there's the tricks what you do about it. And we must do about it something. That's easy fix. Use operational amplifier and feedback. So fundamentally, if you have any, say, decent operational amplifier, whatever you put here, your neighbor's cat, this circuit tries to minimize the voltage. So the output is driven such that this voltage difference is 0 when you have a negative feedback. This is covered already, right? Good. So whatever the impedance here is, or whatever the circuit is here, it tries to do that one. Okay, so in this case, that whatever circuit is this B-class amplifier. And there we have the load. And we take the feedback fundamentally from here. So ideally, on a paper, this is perfect. So this one actually makes sure that the crossover distortion doesn't happen. Okay. Minor thing here. Well, it's in paper this looks great, but still, you have the dead zone here. So let's make a, so we have a volts in, actually voltage. If you have sinusoid voltage input, okay, something like that. So this is the positive cycle, negative cycle, and then somewhere here we have that dead zone. So that's plus V gamma, that's minus B gamma. If you're taking a look at the operational amplifier output requirement, okay, for positive cycle, now I actually could use a colored, yeah, well, I'll do it without. So that's the input signal, and that's also the desired output signal since that's a follower. But still, the operational amplifier output signal, to get 0, you need to have that VBE voltage or V gamma voltage on output. Okay. There. That's the operational amplifier output, which is same as the base output. This actually requires, the negative cycle requires that we have the V gamma here. Oh, the operational amplifier actually should start here. As a function of time. And now, how fast you can go from something like plus 0.6 volts to minus 0.6 volts. That depends on the slew rate of the amplifier. So in practice, this basically does not quite follow that one. It reaches the required voltage somewhere here, which means that it still has some distortion in here. Some crossover distortion is still remaining because of the slew rate. But this is already at least decade better than the original. Good. Okay, we covered that one. Good. Slew rate limit. Okay, that's the other way of actually going over the problem of the crossover distortion. So basically what we do is we have the input signal as we had, okay. And then we have a, oops, balancing power supplies. So this is a model. We don't put any batteries here. Could we? Okay, to overcome the fact that we have the voltage drop here, we actually add some V gamma here. Practically, this is same as wondering the VBB or 2. Are you considering the VBB as the base to other base here? That one, right? The turn on voltage. Okay, but anyways, so you need to actually overcome this voltage drop to turn this one on, and also that one. Okay, which means that both at this when you have everything really designed right on, this one shifts the crossover. If it was like that, it actually shifts that one here. So on optimal solution, you have the positive side like that, and also the negative side. It started here, but you shift the transfer curve like that. Okay. And at some point, of course, that's saturation for that transistor here. Okay, so at that point it saturates. There, that's the transfer curve. So that's the fundamental idea of how to balance or get rid of the crossover distortion. And of course, now if we have totally eliminated the crossover distortion, we can actually run it with even better by running it with the operational amplifier to make it really linear. So this is linearizes everything, and don't need that good matching of the beta anymore. Okay. So, but anyways, I think this is a good place to end. So it's getting about 12 o'clock. And we will be continuing from this part on Thursday. Okay, yeah, so that one. Okay, good. Then I have some office hours, just in case you need help on the, theory, or preferably on you have the assignments now, and then homework exercises. If you need some help, I will be available tomorrow. What was the time? There was the timetable somewhere.